Hi, my name is Bonnie Hurwitz from the University of Arizona. Today, I'm going to talk about open science data standards and a project I lead called Planet Microbe as an example of redeveloping reusable data practices in the scientific community. Today, we're going to start our story as data scientists in the far reaches of the universe. At the beginning of our journey, we look at the data and only see the tip of the iceberg and perhaps just a small data set that we have collected. But we know that the story goes deeper, and as we start to collect other data sets, we can see new dimensions and perspectives that give us enough detail to form and shape our story. In the ocean sciences, these perspectives come from varied data sources, such as physical chemical properties of the ocean, organisms that are both big and small, and global ocean processes and current systems that drive changes. The problem is that these tantalizing data sets are maintained by different experts in different formats with no way to interconnect them. Even with a single data type like metagenomics data, we often find ourselves drowning in the deep, dark waters of data cleaning and integration to get to the point where we can actually perform global analyses. In particular, no matter how we serve up the data with beautiful interfaces, no technological innovations can fix these larger curation issues that need to be addressed prior to integrating the data. For example, when my team went and collected all of the world's metagenomic data for ocean sciences on the microbiome, what we found was that there are about 35,000 different marine metagenomes. And then of those, there were 7 different formats for latitude and longitude, some that were in the same field and some that were in different fields. We also found 27 different collection dates and time formats, and then 830 other fields that were duplicated and in unstandardized formats. In addition, the datasets oftentimes did not have common units, which meant that all of these datasets, although accessible, were not actually able to be put together into a global analysis. To fix these issues, I oftentimes like to think of it like baking a cake. So oftentimes we can think of different kinds of data as different ingredients for the cake that we want to bake. So we might have eggs, or flour or sugar, and all of those same ingredients can be combined in many different ways to have many different kinds of cake or many different insights into a particular scientific data set by combining them in different ways.
Recently, new efforts in FAIR data have emerged. Data are fair when they are findable, accessible, interoperable, and reusable, not only to humans, but also to machines and machine agents for advanced algorithms in machine learning. To promote fair data practices for the microbiome sciences, the National Microbiome Data Collaborative was formed. This effort focuses on developing community-driven standards that are curated and high quality, as well as being interoperable across data sets. This effort also aims to make microbiome datasets open and accessible. Recently, the Department of Energy funded efforts to harmonize environmental datasets that you can hear more about at the NMDC website and through the Twitter handle. This effort is open to any community. I lead up a team for harmonizing ocean science microbiome datasets called Planet Microbe. Planet Microbe was originally established as a data integration project to reconnect omics and biogeochemical data from ocean samples collected on the same research crews, but dispersed across research teams and data repositories. To do this, we leverage ontology terms to annotate, standardize, and make each of the datasets' metadata fair. Ocean science datasets have been collected by a variety of efforts, from large-scale research cruises to citizen science. And in each case, each project has developed their own metadata with varied semantics. To use these data sets together, we have to put them in a common framework with similar definitions. For example, an omics dataset comes from a specific water sample that was derived from a sampling event and was part of an expedition. Along the way, each of these components has a variety of measurements and data that need to be accounted for and harmonized across projects. To do this, we are leveraging and extending the Open Biomedical Ontology, or OBO ontologies. For example, if we had a value for nitrate, we can describe the concentration using the environmental ontology and use consistent units using the units ontology, and cite the instrument or protocol that was used for collecting the samples using protocols.io. This allows researchers to use data sets across projects and also determine if the data are consistent with the data that they are collecting for their project. We are currently using 7 different ontologies from OBO, and we have created our own unified Planet Microbe ontology that connects diverse data sets and drives our in-depth comparative analysis. Once we have harmonized the data, we use frictionless data packages to collect data and metadata in a single place, which is called a data package.json file. So the data can be shared and repurposed across systems, and the data are a product in and of themselves. To make these data actionable, we integrate the data packages into an interactive search interface on our website. Through this search tool, users can find data based on common semantics or using the map, and then add the data to their cart and run analyses. In order to run jobs for the users, we leverage NSF-funded cyber infrastructure resources. For example, we use the data store from Cyberse, which is a cloud-based storage platform built on iRods that is redundantly backed up in the cloud. Cyberse also provides authentication services, so you only need a single sign-on using your Cyberse account. For compute, we leverage the $30 million Stampede 2 supercomputer at the Texas Advanced Center for Computing. Stampede 2 has almost 370,000 cores that are available. And because we use these existing resources, there's a lower cost of development and maintenance for our project. We maintain just a small code base and a single small web server in order to implement Planet Microbe. Finally, the tools that we have developed for our website are containerized using Docker or Singularity, and we make these tools open source. So as the tools are containerized, the source code is compiled and built and packaged in a way that can be run on any system. Our containers are also linked to the Planet Microbe interface using JSON files that dynamically describe the inputs, outputs, and parameters for each tool. To use these tools, we developed a user dashboard so that users can run jobs, track their progress, and share results and analyses with colleagues. Planet Microbe is just one use case that demonstrates how open science can be implemented and pushed forward through common data standards, frictionless data packages, and containerized tools. These resources build on existing standards through the OBO Foundry and work in the National Microbiome Data Collaborative. We also rely on shared compute resources at Cyberse to make high-performance computing available to anyone. With that, I'd like to thank my team for developing the platform and integrated data sets, and my collaborators, Ed DeLong and Alicia Wood-Charlson, for all of their insights and efforts on the project. Thank you so much for listening today.